Okay, let's get started. So this is meant to be useful for you, so feel free to ask questions. You guys already have the answers to all these problems, so really the purpose of this is to explain things in more detail if you have questions about the answers. So I'm not gonna go through all the problems because some of them we haven't covered the material yet for, and probably there won't be so many problems on them. But let's go through some of them. So number one we already did in class, but let's review that just to get started. So here once again, the question is, we put in some gel. What would be reasonable T1 and T2 values of the new mixture? So the thinking behind that is when we add the gel, there's going to be less tumbling, right? So we know for T2, we're moving down this part of the curve. Okay. So the T2 has to be less. So it can't be this, it can't be this. It still could be any of these guys, right? But we also said that T2 has to be less than or equal to T1. So therefore, it cannot be this guy, and it cannot be this guy, right? Is that right? Okay. So now we're down between D and E. Okay. When we did the lecture, we said it could maybe be either of them, but in this quiz, it's a forced choice, so it's making me think a little harder about which one it actually could be. So remember the T1 curve goes like that, right? And the idea is, so we really have to think about where would be on this curve, because that's going to determine whether the T1 decreases or increases. If we're here on the curve, it's going to increase. It's going to decrease. If we're here on the curve, it's going to increase. Okay. So what can we use to think about where we are on the curve? Where on the curve are we more likely to be? Are we likely to be out here or over here? Yeah, we're likely to be out here, right? Because it's a liquid. All right. So if you're given a forced choice, you're much more likely to be in this region, and therefore it's got to be D. Okay. The T1 should also decrease. So that's how you think about a problem like that. All right. Okay, let's look at the, this was the one that was in the lecture that I skipped over, so let's go through it. So we talked about this coupling ratio between blood flow and metabolism of 2 to 1, okay? And now we're saying what happens if that ratio goes to 3 to 1, what's going to happen to the magnitude of the bold response, okay? So now going from 2 to 1 to 3 to 1 means that for every increase in some metabolism, I'm delivering more blood. Right, so there's going to be more oxygen, there's going to be less deoxyhemoglobin, so there's going to be less dephasing, so the signal should go up. Okay, so I should expect that the magnitude of the bold signal should increase. Okay, so that's all that question is asking for. Any questions so far? Okay. Okay, so here's one where, and so for these things, you're given that gamma over 2 pi is 4,000 hertz per Gauss, just to make the calculations easy. So definitely, I think we will state that on this. For at least all the problems that I'm doing, that's the assumption that will be explicitly stated, 4,000 hertz per Gauss. Okay, so that's what we're going to use. So now we're going to say that we're in a magnetic field of 3 Tesla. We have spins at 2 locations, 0 and 10 centimeters along the z-axis. Okay. And then I have a 4 Gauss per centimeter gradient field. And so I start the spin spinning at t equals 0, right? So this at t equals 0, the spins are aligned, right? The one at the isocenter is going to just stay there, right? Because it's not having any extra field. But this guy is going to precess, and the question is, how long will it take till it precesses back to the pointing in the same direction? Okay, so essentially, how long does it take to go one cycle like that? So that's what that question is asking. So we want to know the frequency of precession, right? So the frequency of precession is just going to be F equals gamma over 2 pi times the gradient, okay? And then we want that So we want f to be the frequency, and we want to leave it on for some amount of time t, right? Because that's going to tell me how many cycles I go, all right? And we want that t to give us 1 cycle. All right, so it's processing. Like if it's processing at 1 hertz per second, then I'd have to wait 1 second for it to go back 1 cycle. Okay, remember frequency is cycles per second, right? This is 1 cycle, so if I take cycles per second and multiply it by seconds, I'll get cycles. All right, so that's what we want to set up. So we want to set up that equation. So we have gamma, so we have 4,000 times 4 equals 1. Okay? And so, let's see. Oh, and then I forgot something, right? It's actually g times delta z, right? Okay, because depending on how far out it is, it's going to spin faster, right? So I need that 4,000 times 4 times 10 is equal to 1. Okay? So this is just that times the t. So t equals 1 over 4 times 10 times 4,000. Right? And it turns out that that's 6.25 microseconds. Okay. So the closest answer would be that one. So what this problem is really sort of testing you on is understanding that when you're in a gradient field, you spin faster. And so knowing that where you are in the gradient field determines your frequency of precession, that was the concept you would need to know for this problem. Okay. Any questions on that? Okay. All right, next question. Consider a spin warp pulse sequence designed to achieve an FOV of 24 centimeters in both x and y directions with 1 minute resolution in both directions. Maximum available gradient is 5 Gauss per centimeter. So the user reduces the FOV to 12. What needs to change in the pulse sequence? Assume that the sampling period, so this is the delta t, doesn't change, and that everything else is held constant. Okay. So let's work through this. So without even looking at the answers, let's just think about what's happening here. Okay. So the FOV in the x direction has gone down by a factor of 2, right? So what does that mean about my delta kx? What should it go up by? Factor of 2, right? So it's got to go up by a factor of 2, right? Okay. So if I'm thinking about sampling in k-space, this is my kx and this is my ky. If originally my sampling was like that, now I'm saying the delta kx is going to go by a factor of 2. So I'm going to be sampling here and here, right? So this is my new delta kx. All right, so that's one thing. And then I haven't changed my resolution, right? Or has my resolution changed? Okay, so let's ask about resolution. So it says nothing else has changed. So the question is, did the resolution change? So in this case, the resolution, we're told that everything else is held the same. And so we're going to assume that the resolution which we were given doesn't change, right? So no. So that means the WKX is the same, right? Okay, so how far I go out is the same. Okay. So therefore, if I think about that readout gradient, it's got to be on. So let's say I use the maximum gradient of, let's say the time, the WKX is the same, but the delta KX is different, right? So what does that say about how many readout samples I have? Has it gone up or has it gone down? It's gone down, right? Because the amount of k-space I'm trying to acquire is the same, but the spacing has doubled. So number of readout has gone down by a factor of 2. Okay? So we know that D should be correct. Okay? So that would be correct. And then what about the length of the readout gradient? Delta T is the same, right? But I've reduced the number of samples by 2, so therefore the length should also go down. Okay? So this is also correct. And so now we're just left out with the amplitude of the readout gradient. Okay? So remember, the delta kx is just gamma over 2 pi times the amplitude of that gradient times delta t. Okay? Delta t stays the same. This has doubled. Therefore, we better double this one to get that to double. And therefore, the gradient amplitude will double. Okay? So for that one, the answers would be D, F, and G. All right? So this is slightly more involved, but it's basically, you have one thing to realize is the phasing code is not involved at all because we've only changed the x direction. And then it's just figuring out, did things go up or did they go down? All right. Question? Yeah, so that's the assumption that x is always readout and y is always that is the assumption. Okay. Any other questions? Okay. Number 5 is a spin warp pulse sequence is designed to achieve an FOV of 24 centimeters in both directions. The maximum available gradient is 5 gauss per centimeter, and the pulse sequence is designed to take advantage of this. So behind the scenes, someone reduces the gradient amplitude in the phasing code direction by a factor of 2. Okay. You're aware of this change and reconstruct your image as usual. If everything else is held constant, what are the expected effects on the image? Okay. So what is this going to mean? Basically, remember the phasing code gradient, we had a different number of phasing codes, right? And this sort of GYI, this spacing here, let's say there was some amount of time t, this led to my delta ky, right? And then this whole thing here led to my wkx, okay, so how far I go in k-space. So the question is, let's say someone this is what we thought we programmed, and let's say someone just came along and made that half as big. And you didn't know that, right? So, but you just reconstruct your image as usual. So if those amplitudes all decrease by a factor of 2, what's happening to my delta k's? So I'm not moving out as far, right? I thought I was moving this much, but I'm only moving half as much, right? Nothing else has changed. So therefore, my delta ky is going to go down by a factor of 2. Okay, what does that do to my FOV in the y direction? Makes it go up, right? So we know the FOV in the y direction should double. Okay, and we don't have to worry about the x direction because we didn't mess with that at all, and we don't have to worry about this either, right? So now we're just left with the resolution. So I've cut my gradient in half. So am I moving farther out in k-space or less in k-space? Less, right? So I'm not going out as far. So therefore, my wkx has gone down by a factor of 2. So my resolution has gone up by a factor of 2. So that's all right. So these are the basic things that for spin warp, that just understanding really it's just delta k and FOV, WK and resolution, and then how those relate to the gradients. Right. Any questions? All right, we're going to skip the RF ones because we haven't talked about that. We're going to skip the phase angiography one because we haven't talked about that. We're going to skip the diffusion one. These last questions, we'll do 10 and 11, and then if people want to, we can do some on the 2017, or we can leave that till Wednesday. So let's do these and then just make a decision. In order to make MR images more quickly, we need to decrease the TR value. When TR is reduced from 500 milliseconds to 5 milliseconds, one of the principal issues we need to deal with is A, B, C, or D. Okay. So let's think about this. Is this going to affect my aliasing at all? No, right? It has nothing to do with how I'm covering K-space. In fact, the primary thing it's going to do is, we're talking about saturation recovery. So if I wait 500 milliseconds, I have quite a lot of signal to deal with. If I only wait 5 milliseconds, there's not much time for the signal to recover. Okay. So of all these, the correct answer should be C. There's a loss of signal noise ratio in the raw data. We really haven't talked about visualization of contraction of the heart. So yeah, let's skip that. So, okay. So I think the questions we've gone over are the only ones you actually have had enough material to do, and that reflects we're a little bit behind schedule this quarter, and we missed a day, and so your quiz 2 will reflect that. So when you're looking at the previous quiz 2s, if you go, oh my God, we haven't really covered that, the quiz 2 will reflect the fact that we haven't covered some material, or if we've covered it, it's in less detail. Okay, so don't worry about that. So now let's take a vote. We can continue going on to 2017, or we can stop now and do that on Wednesday. Who would like to continue? Okay, and who would like to stop? Okay, so unfortunately, we're going to continue. Okay. You can always leave and watch the video. Okay, so this is the 2017 one. Okay, so bring up the answer key so I don't say anything wrong. Okay, so this is similar to the other problem, which we're talking about T1 and T2, except now we're raising the temperature of the liquid from room temperature to 50 C. Okay, so the first question in all these questions is what's happening to the tumbling rate. So as I heat up the liquid, is the rate going up or down? Obviously it's going up, right? Okay, so the rate has to be going up. Okay, so now we can go back to these curves and go, okay, the T2 curve goes like that as a function of rate. So therefore, I must be moving like that. So T2 must increase, right? So I'm down to these two options. Okay, and now it's very similar to the previous question, which is the T1 curve goes like this, right? And we already said as before, we're in a liquid, so we know we're probably in this regime. And so as the rate's going up, we're probably going this way. Okay, so the T1 should also increase, and therefore, yeah, and that's the solution that's there. Yes, question.
So besides like heating or adding a gel, what are some other scenarios that
Yeah. Right. Well, I mean, it could be, if somehow, I mean, they're all related to density, right? So anything that changes the relative density or the energy, those are the main things. And so, you could imagine putting in something that's not a gel, some calcification or freezing something, which changes both the density and the temperature. So as long as you have that picture in mind, and this isn't a physics course, so we're not going to really challenge you on what changes tumbling rate. So it'll be really obvious which way it goes. Yeah. Okay. We are going to skip the phase angiography one. We might pick that up on Tuesday. Let's go do number 3. Yes.
You said that T1 is bigger than or equal to T2, but then if they're equal, that at this point was So T1 should be bigger than T2 at all times.
Yes, they can be equal to it. Yeah.
But then doesn't it mean that they are gonna close each other? I mean,
Um,
should they be in the limit equal?
They could be in the limit equal, yeah. I mean, they could just follow each other. Yeah. So for this question, right? I mean, it might be like since they are equal, it's an acceptable answer, and it's the only answer that makes sense. Yeah. But in general, yeah, the constraint is that T2 must always be less than or equal to T1. So yeah, it would be okay if, I mean, if the curves were like this, right? Okay. Okay, any other questions? Okay. Let's look at number 3. We're going to consider a spin warp pulse sequence to achieve an FOV of 24 centimeters in both the x and y directions. This is very similar to the one we just did, but let's just go through it because I think it's useful just to, the more of these you do, then by the time you get to the quiz, it's like, oh yeah, you know, it's just old hat, okay? So a lot of this is just getting used to the format of the questions. So once again, the user doubles the FOV in the x direction. Okay. So right away, we can rule out all the phasing code ones, right? So we just figure, oh, I don't have to worry about these guys. Okay. And then the hint when you says you may pick more than one, it probably is you probably should pick more than one. Okay. So that's another test taking thing. So then we go and it's essentially the same. So we basically go, the user doubles the FOV goes up, so that means delta K must go down, okay? And since delta T is kept the same, we know delta K is gamma over 2 pi G times delta T for the readout, all right? So therefore, delta K goes down, therefore G must go down. Okay, so this one up by a factor of 2, this one down by a factor of 2, therefore the gradient must go down by a factor of 2. Okay, so the amplitude of the gradient will be halved. All right, and now we haven't changed the resolution, so the resolution is the same. Therefore, delta Kx is the same. Okay, so we have the same width in K space, but delta K has gone down by 2. So the number of samples must have doubled, right? So the nx has gone up by a factor of 2. So we know this number of samples will double. And since delta t is the same, that means the length will also be doubled, right? Oh, sorry, I circled the wrong one. So it's basically the same thing, right? And that is actually the solution, right? C, E, and H. All right, question? Yeah, that's probably not great nomenclature. It's basically the duration in time. Yeah. Yeah. Okay, any questions? All right, one more of these questions. Well, this is a case where it says you may pick more than one, but you probably shouldn't. So it's not always that you should pick more than one. So let's look at this. Here, it's essentially the same. FOV of x is doubled. But now the key thing is this is the same. So that's going to change things a little bit, right? Okay. So the question is, what needs to change in the pulse sequence? So delta K must go down by a factor of 2, right? And delta K equals gamma over 2 pi G delta T. This is the same, so this gradient still has to go down by a factor of 2. So we can certainly circle that. We know we don't have to worry about these. So now it really comes down to, is the number of readout samples double or halved? It's sort of I've already given you the answer, right? The number of samples is the same. So it can't be these guys. And the length is the same because the number of samples times delta t is the same. So it can't be those guys. Right? So in some ways, it's slightly more confusing, but in some ways it's much easier. All right. Any questions on that?
How would we approach a problem like this if it was changing the y?
Yeah, that's a good question. You would then be basically, it would be the same thing. You would be probably, one thing would be said, and you might be asked about the, like, for example, let's take example of, you know, let's say we had, I told you this went up to a maximum gradient of 5 and minus 5, right? And so in this case, since I'm constrained to the maximum gradient, then I might, whereas I might say, okay, now you're not constrained by that maximum gradient, and I might ask you about, like, what's the maximum amplitude of the phase encode, right? So in that case, you know that that max amplitude would be related to WKY, right? Because that's how far we go in k-space. So I would tell you something about the resolution might change, in which case you'd say, okay, let's say the resolution changes, and that's going to change my WKY. If I keep the duration the same, that means I've got to change that amplitude. And that would be the sort of thing you'd be asked. Yeah. So the main difference for the phase encode is there's really no delta t, right? So I'm going to have to tell you something about the duration of the gradient. Yeah. Or else I can either keep the duration fixed and let the gradient change, the amplitude change, or I could keep the amplitude change fixed and change the duration. So that's really the only two things. So in some ways it's similar logic, but just slightly different nomenclature. Any other questions? Okay. We're going to skip this guy and this guy for now. Okay, number 7 is you're asked to have gradients that take you out in k-space to the location 1, 2. All right? And the maximum gradient you have available to you is 5 Gauss per centimeter. So what's the minimum width you can use to get out? You know, how fast can you get out to that? Okay. So the first question you have to ask is, which is going to dominate? Is it going to be moving out in ky or kx that is going to really constrain my problem? Kx, right? Because I've got to get farther out in kx. So I just need to look at kx, right? So then I just have gamma over 2 pi times my 5 Gauss per centimeter times the time it's going to take is equal to the bigger one, which is 2. Okay. So then I say t is equal to 2 over 5 times 4,000. Okay. I think that's what I have. And that's equal to 1 over 10,000. Yep. So that's the correct answer there. All right. So the key to this was just realizing that the farther out, given 2 places in k-space, the one that's farther out is going to require more area, so that's going to determine the time it takes. Any questions? Okay. You're asked to design a spin warp readout gradient to achieve FOV of 25 centimeters and resolution 1 millimeter. Maximum gradient strength is 5 Gauss per centimeter. Sample period is 10 microsecond. What should be the amplitude of the readout gradient? Okay. So we know the FOV is equal to 25, right? So therefore, delta kx is just 1 over 25, right? And that's just equal to gamma over 2 pi times the readout gradient times delta t. Okay. So now I just solve for gxr equals 1 over 25 times 4,000 times 10 e to the minus 6. Okay? I use e to the minus 6. It's not e to the minus, it's just the MATLAB sort of notation, right? Okay? Let's just correct that just to make sure there's no 10 to the minus 4. Oh no, 10 to the minus 6, right? 10 times 10 to the minus 6. right? Okay, just so there's no confusion. And so it turns out that if you go through and solve that, you get 1 Gauss per centimeter. All right. And so one thing I want to point about this question is oftentimes in these things there's information that you didn't need to use. Like I didn't need to use this, and I didn't need to use this, right? So although you're provided with, so I only had to use half the information I was given. Right? So it's not always that you're going to use all the information. But in this case, especially for spin warp, the FOV directly relates to the gradient amplitude. All right, any questions about that? Okay. So let's look at the phase encode. So now this is an example here where you're given the gradient strength, but you don't know, you asked to figure out the minimum width, okay? And in this case, since you're given the maximum gradient strength, which of these is the more important one? Is it the FOV or the resolution that you care about? So that's the important thing for this problem, right? Because both of them are related to the gradient, but you're told the maximum gradient strength available. So what does that tell you? Which parameter? Is it going to be, so this is going to change your delta K, Y, and this is your W, K, Y. Okay. So which one should I design for? Yes, resolution, right? Because this is this one. It's how far I go out, right? The maximum tells me how big I can make that gradient, right? So it's saying the biggest I can make that gradient is it can go 5 this way and -5 in that way, right? That's the biggest I can make it either negative or positive, right? I can't go more than that. So that determines how far I can go out in k-space, right? And then I have it on for some amount time t. Okay? So I know that the WKY is equal to 1 over 0.1 centimeters, right? This is 1 millimeter. So that equals 10. And that should equal gamma over 2 pi. This distance here in gradients is 10 Gauss per centimeter times t. Right? So in this case, the math is pretty simple. It's just t equals 1 over 4,000, which is 250 microseconds. Okay, does everyone understand why we use the WKY instead of designing for delta KY? Anybody? Okay. So the reason why we didn't do the delta KY is because there's no constraint on that, right? Because I could make that, the delta KY is pretty small, right? And therefore, it doesn't, I mean, I could make the time anything. There's lots of combinations of timing that would get there because I don't need the whole 5 Gauss per centimeter. I can pick anything less than 5 Gauss per centimeter and still get the same delta KY. So there's no constraint there. So I have to pick the one that has the constraint. Yes?
So for like the gradient that you chose, like 10.
Yes. Okay.
So is maximum gradient, I kind of confused like the maximum gradient and like,
Yeah.
I don't know if that makes sense.
Okay. Yeah. So let me try to answer that question. So the maximum gradient is simply the largest I can make the pulse. Okay. So for example, it means in one case maybe I play it out at 5 Gauss per centimeter. Okay. So it's this area here, right? So this would move me out in a very positive direction that way. Okay. And then another time I might play something that's at -5 Gauss per centimeter. And this would move me out in the opposite direction. Okay? And then this is the WKY here. That's how far out I went in k-space. Yeah. So the 10 is just saying I went 5 in one way and -5 in the other way, and so the extent is 10. That's how far out I moved in terms of gradients. Yeah. So you can think about it, I mean, this is a shortcut once you get used to it. If it's sometimes helpful as you're sort of doing these problems to, I mean, it's okay to maybe just think about it like this. You say, okay, I have to move this way, and I have to move that way, and So the other way you could do that is this could just be, instead of WKY, I could say, well, WKY over 2 is KY max, right? So instead of using the WKY, I could divide it by 2 and say, I'm only moving out this far in K space. And then, so that might be simpler to think about. Okay?
How did you get your gradient though? So you have like 10 equals 4,000 times 10 times 2.
Yeah, so this 10 is just 1 over 0.1 centimeters. So that's the WKY. So that's from the resolution. So the WKY is equal to 1 over the resolution. Yeah. So that's, so yeah, you always go from, so this is what determines my WKY. Okay? All right, any other questions? Okay. We're going to skip the RF pulse one. Yep. And then let's look at, let's see, we have 11 and 12. Okay, yeah, we have just 2 more problems to go over. This one we were given a spin warp pulse sequence in which the gradient amplitude is 0.1 Gauss per centimeter. The sampling period is 10 microseconds. Desired resolution is 1 millimeter. Consider an object located at x equals 0. Okay. The object exhibits off-resonance behavior and processes at a frequency that's 100 hertz higher than the assumed normal frequency at the isocenter. In the reconstructed image, this object will appear to be displaced from the isocenter. What is the magnitude of the displacement? So let's think about what this problem means. So I have a spin at the isocenter, right? So it should just stay pointing that direction the whole time, all right? And therefore I know it's at the isocenter. But what happens is, for some reason, it decides that it's going to precess at 100 hertz. Okay? So it's going to appear, it's going to do the same precession as a spin from some other place in space. Okay? So imagine I have some gradient on here, and I'm saying the readout gradient is 0.1 Gauss per centimeter. Okay? So the question is, it's at some, it's going to appear, it's the frequency, so this is, this is like hertz, so this is a spin here in the presence of some gradient would precess at 100 hertz. Okay? So the question is, what is this distance x? How far do I have to go out before a spin precesses at 100 hertz? So that's all it's asking. So therefore, it's just, we know that the frequency of precession is just f equals gamma over 2 pi times the gradient times where we are in space, okay, at x. And so we're just solving for this delta x, okay? So we're saying, because this is equal to 100, this is equal to 4,000, and we're given this is 0.1, okay? So we're just saying that the x, or the delta x in this case, is just 100 over 4,000 over 0.1 equals, let's see, does that work out? Must be missing something. Let's see, let's look at the answer. Oh, okay. It's in millimeters, that's what got me confused. All right, so this is 0.25 centimeters, right? Which is equal to 2.5 millimeters. Okay, so it's just saying that if I'm out at 2.5 millimeters away from isocenter, I'll be precessing at 100 hertz. And therefore, a spin at isocenter that's precessing at 100 hertz will appear as if it's moved. All right. Any question on that? Okay. Okay, one last question, which we already did in class, right? So we don't have to do this, right? Unless someone wants to go for it. Okay. So, so I think that's it for today. So there will certainly be questions like this on quiz 2. So just getting used to the format, I think, is useful so that you're not surprised by the format. And then what I might do is, since you've already gone through this, in my experience, the best way to prepare for quizzes is just maybe give yourself a mock quiz. You know, take some of these questions without the solutions, and just try 10 of them and just get yourself geared up to take it. Okay, it wouldn't take very long to do it, and it's probably a best use of your time. If you just look at the answers, you're not. It's not going to get your brain in shape for the quiz. Okay, so you really have to try it without the answers. Wait a few days till you've forgotten what we talked about, and just try it, and that will actually get it into your brain a lot better. All right, anything else? Okay, so I'll be here to answer questions about the homework if anyone has them.